For exercise 6E, question 6, page 82, again, you need to read the question carefully. We've got a particle moving in a straight line, and it's a displacement function, and it's an exponential displacement function. So my first thought is, in an exponential function, the displacement is going to be positive the whole time. So to get an idea of what it looks like, you could use your graphics calculator. Getting the view window right's a bit tricky. I prefer Desmos because you can adjust the screen much more easily. So we've got our formula, we know that it's an exponential function, therefore, and we see that the time is greater than or equal to 0. Find the velocity and acceleration functions. So velocity is the rate of change of displacement. So we're doing the derivative of displacement function to get a velocity function. And hopefully this calculation is pretty straightforward. I always, when I differentiate the exponential function and get multiplied by minus a fifth, if I've left space, I can write it in the front, or otherwise I write brackets just to emphasize it's multiplied. Just pausing to look at the function. When I drew it on the calculator, it was close to a straight line. So if you just look again at that original function and you think it's 200, e to the negative t on 5 is actually, you divide it by to make it a positive power. So this displacement function equals almost a straight line. So that's the first thing. As t gets large, 200 over a large number, if it's a huge number, will approach 0. And so the function approaches a straight line with a gradient of 100. So the next thing is just to emphasize that you understand that the velocity function of a displacement time graph, let's say that again, that finding the gradient function of a displacement time graph gives you velocity. So if I have the instantaneous gradient here, then the gradient is the difference in the vertical direction, which is the difference in the displacement, divided by the difference in the horizontal direction, which is the change in time. So the meaning of the gradient of this graph is velocity. So the displacement time graph, the gradient of the displacement time graph is velocity. And in a similar sort of reasoning, we could explain if we plotted velocity against time, then the gradient of a velocity versus time graph will be, so if this is velocity, then the y, the vertical gradient, the vertical axis, is the change in velocity, and the horizontal axis, which we often have the variable x for, is change in time. The definition of acceleration is rate of change of velocity. So just hope that helps you to understand why the second derivative of a displacement function gives you acceleration. So let's do that now. We're finding the acceleration, we're just calculating it. So we've found the velocity function and we've found the acceleration function, and we'll use them to find the initial position, velocity and acceleration of the point P or particle P. So initial just means at time equals 0, so we've got to put it into the displacement function. And 100 times 0 is 0. 200 over e to the 0, e to the 0 is 1. So the displacement will be 200 metres. The initial velocity, if we put that into the velocity function, the 100 is there. And again, if we subtract 40 divided by e to the positive t on 5, but t is 0, so that's e to the 0, that is 1. So it's going to be 100 take 40, which will be 60 metres per second, which reminds me I haven't put the displacement units there. Oh, yes, I did, the metres. And acceleration initially, when time is 0, we find our acceleration function. And I hope you notice that the labels are really useful here. 8 times e to the power 0 will be 8 metres per second squared. Part C asks us to discuss the velocity as t approaches infinity. So we go to the velocity function. Here it is. It's 100 minus I squeezed up the screen and I put the minus 1/5 in the wrong place. So now I'm looking at the velocity function here, which I've just corrected. And I'm going to look at when t approaches infinity. So 100 minus 40, and it's e. Now if t is infinitely large, a huge number divided by 5 is still a huge number. The negative just means it's divided by e to a huge number. So I've got 40 over e to a huge number. We'll put infinity there. And 40 is insignificant. Minus 1 over a huge number, that's going to be minus almost nothing. So when t approaches infinity, the velocity function is going to approach 100 from below because we're taking a tiny number. So from below. From below 100, that's what it means. Part D, sketch the graph and the velocity function. So if we're going to graph the function, we need a velocity, the velocity function against time, and we know that it's going to approach the horizontal asymptote, which will be y equals 100 from below when t is very large. So we just do a little dash when t is very large. We know that the initial velocity, if we look back at our earlier work, was 60 meters per second. So at 0 time, the velocity was 60 meters per second. So I really need a bit of a scale here. So if that's 100, this must be about 50. So here's about 60. And it approaches it and it never touches it. So we've got to show that it's an asymptote. So it is just a sketch, but you do need a bit of a scale, and you always need to label your asymptotes, and your axes should really have units there. And you've got to have some indication of scale. So we want to give the impression that t is very large. So I might go 100, 200, something like that, just to really show why it's becoming asymptotic to 100 from below. Part E, we're asked to find the time when the velocity is 80 meters per second. So we look at the velocity function and write it down, and we substitute in that it's going to equal 80 centimeters per second. So I've just realized that when I've written units, I've written meters. So I'll quickly go back and make sure that they're centimeters. Here we go, that should be centimeters per second. Now, as I wrote out the formula, I nearly wrote it as a positive power of E, but as soon as I have an E in my equation and think that I'm going to solve for T, I'll probably have to find ln of both sides to simplify this function so that I can find T. So if I simplify it, I'm going to add 40e to the minus 5t to make that positive. And if I take 80 from both sides, 100 take 80 is 20. If I divide both sides by 40, I'll get e to the minus 5 on t equals a half. So if I take ln of both sides, I'm going to use a couple more rules. ln is inverse function to exponential function, so the power will be the answer, 5 on t. I know that ln1 divided by 2 is the same as ln1 take 2, so in my head, ln1 take ln2. ln1 is 0, so it's going to equal minus ln2. Multiply both sides to make it positive, and so I will get, I'll just rub out the negatives. So t is going to equal, so t comes up to the numerator, divide both sides by ln2, t equals 5 on ln2, and I look back at my original question, does it say exact? No, so I could work out the time on my calculator. And I've just had a quick look at the answer in the back of the book. My answer's not the same, so one of us is wrong. It'd be interesting to hear whether it's the back of the book or whether there's some calculation error here.